Yeah, great. Thank you for coming to my talk, everyone. So today I'm going to talk about some joint work that I carried out with Robbie King, who's also here today, looking at a really classic problem in classical topology and its connection to quantum complexity. What we show, the main kind of takeaway result of our work, is that this problem that you can write down, specify, describe without any reference to quantum mechanics at all is actually completely characterized by quantum complexity classes. So for those of you who are familiar with quantum complexity classes, what we show is that this problem is QMA1 hard and contained in QMA. For those of you who aren't so familiar with quantum complexity classes, don't worry, we'll explain exactly what this means in the talk. Okay, so there's this very classic problem in topology that is characterized by quantum complexity classes, but what is this problem? So the problem we're going to be interested in today is what's known as the homology problem. And in homology, what we're interested in is holes in some space. And today we're going to stick to a very nice, simple problem in homology. We're just going to ask, given some space, does it have a hole or not? And in particular, we're going to ask, does it have an L-dimensional hole, where we let the dimension of the hole grow with the size of the input to the problem. We're interested in this as a computational problem, and dealing with continuous manifolds computationally is a little bit tricky. So we're going to not worry about continuous manifolds, and instead worry about the homology problem restricted to simplicial complexes. Where a simplicial complex is, you can think of it as kind of a discretized version of some manifold. So a simplicial complex is built up out of simplices, where a zero simplex is a vertex, a one simplex is an edge, a two simplex is a triangle, a three simplex is a tetrahedron, and then you can kind of keep going to higher dimensional generalizations of these building blocks. So that's what a simplex is. To go from a simplex, or a collection of simplices, to a simplicial complex, you can just think of it as gluing simplices along their faces. And what's nice about simplicial complexes is that they can be efficiently described. So this gives us a nice way to think about this problem as a computational problem. What we're going to ask is, given some simplicial complex, does it have an L-dimensional hole? Now, I said simplicial complexes can be efficiently described, and there's actually many different ways of efficiently describing simplicial complexes. But today we're going to be focused on a particular class of simplicial complexes where the efficient description comes in terms of a graph that specifies the complex. And this is what's known as a clique complex of some graph. So given some simple graph G, in order to build the clique complex of the graph, you just take all the cliques of this graph G and convert them into simplices in your simplicial complex. So what that means is that the naught simplices of your graph are going to be the one cliques of the naught simplices of your simplicial complex are going to be the one cliques for your graph. So that just means vertices in the complex are the same as vertices in the graph. The one simplices in your simplicial complex are going to be the two cliques in your graph. So again, that just means that edges in the graph are mapped to edges in the complex. Things get a little bit more interesting once we go above edges. So we now have that the two simplices, or the triangles in your simplicial complex, are going to be the three cliques in your graph. And this graph doesn't have any four cliques, so we're not going to go any higher. But in general, you can keep applying this process with larger cliques and higher dimensional simplices, and this will build some clique complex, some simplicial complex. And the key thing here is that this simplicial complex, can have exponentially many simplices in the number of vertices in the graph. But in order to describe the complex, you don't have to give a list of all these simplices. You can just describe the graph.
Are your graphs planar?
No, they don't have to be planar. This one just is because
it's of illustration.
For nice and easy to draw. Okay, so the final, yeah.
You fix the L for the problem, or you?
No, we have to let L grow with the size of the, so as the number of vertices in the graph grows, we also have to let L grow. Okay, so the main problem we're going to be interested in today is, does the clique complex of a graph G have an L-dimensional hole? This isn't exactly the problem we're going to be interested in, because we're going to need to give a little promise on the input of this problem. So we're going to have to promise something about the graph in order to make this problem tractable. But we'll kind of deal with that later. And for now, we can just think about the problem we're interested in is, does the clique complex of a graph have a hole or not? OK, so that's the problem we're going to be talking about today. But why should you care? What's interesting about it? Well, I think the kind of reason people started getting interested in clique homology from in a quantum computing perspective is because it's actually a practically useful problem. So it has applications for a field of data analysis known as topological data analysis, where the idea is that if you have some kind of noisy, imprecise data set, rather than trying to study the data set really precisely, instead you should map the data set to some manifold and study its topology, because that's going to be more resistant to noise in the data than other methods of studying it. And one of the things you might want to ask about some data set is how many holes does it have? So, this is a problem that people in industry are actually kind of interested in solving. And there's no classical efficient algorithm to solve it. There is a quantum algorithm for a closely related problem. It's not exactly the homology problem, but it's morally similar. And it's an efficient quantum algorithm in certain regimes. But those of you who work in quantum computing will remember that a few years ago now, Ewan Tang came along and showed that lots of places where we thought there were efficient quantum algorithms that outperform classical algorithms actually could be run efficiently on classical computers. So she kind of dequantized lots of quantum algorithms and showed that they're actually classical algorithms. One of the few problems that doesn't look quantum, but that resisted this dequantization effect, was this quantum algorithm related to TDA. And that's led to some interest in understanding, is this problem truly quantum? Can we prove that this problem cannot be dequantized? Understanding that question is one of the motivations for this work. Okay, so what was known about the complexity of this problem before we started this project? So back in 2016, it was shown that the version of this problem where you're not given any promise on the input, you're just given a graph,
So for the homology, do you fix the coefficient, or you always, what's the coefficient for your homology?
We'll do it over I can't remember the reals or the integers.
Integers or finite field?
Not a finite field, yeah.
So the integers?
Okay, so in 2016, the version of this problem where you're not promised anything about the input was shown to be classically hard. And what I mean by that is this problem was shown to be at least as hard as the hardest problem that can be checked on a classical computer. It wasn't shown that it could be checked on a classical computer, it was just shown it was at least as hard as the hardest problem that could be. And we are pretty sure, although we don't know 100%, but we're pretty confident that there are things you can check on a classical computer that you can't solve on a classical computer. So this was taken to be kind of a proof that this problem can't be solved on a classical computer. Last year, together with Marcos Criscigno, we showed that, again, the decision version of this problem is quantumly hard. Where, again, when I say quantumly hard, I mean it's as hard as the hardest problem that can be checked efficiently on a quantum computer. So this gives kind of a lower bound of the complexity of the decision problem in terms of a quantum complexity class, which is a class known as QMA1. But it didn't give any upper bound on the complexity of this problem. So it's possible that actually this problem is p-space complete, for example, which is a classical complexity class that is harder than this quantum complexity class. So even though this does give a lower bound to the complexity of the problem in terms of a quantum complexity class, it's plausible that this problem isn't quantum.
Can you say a little bit more about where the classical hardness comes in? Is it because if you have the entire complex data just in your algebra, just compute the homology, right? So where does the
So the point is you're not given the simplicial complex as your input, you're given the graph, and the graph is kind of logarithmic in the size of the complex. So if you just try and run, even computing the complex from the graph itself is hard, but then even if you had the complex, that's exponential in the size of the input, so it's an exponential time algorithm to run the linear. It's an exponential time algorithm to solve if you have the complex in terms of the size of the graph. Just doing it naively, obviously that doesn't rule out another solution, but the naive approach would be exponential time. Okay, there's also the promise version of the problem. So this is the version of the problem we're going to be interested in today. The version of the problem where you're promised something about the input that makes it a little bit easier to solve. And this problem is known that you can check this problem on a quantum computer. So it's known that if someone says, look, this is a hole in the graph, this is a hole in the clique complex, and you have a quantum computer, you can run an algorithm on your quantum computer that will confirm whether or not this hole exists. But this is just an upper bound of the complexity of this problem. There's no known lower bound of the complexity of the promise problem. So what we have is we have a lower bound on the complexity of the decision problem and an upper bound on the complexity of the promise problem. And these are both bounded in terms of quantum complexity classes. But they're slightly different problems, and it's not clear whether either problem can be completely characterized by quantum complexity classes.
Is there a straightforward reason to see why it would be in QMA and not QMA1?
Not straightforward. We actually think it probably is in QMA1, but that hasn't been proven yet. Okay, so what do we do in this work? So in this work, we tackle the complexity of the promise problem, and we pin that down more precisely. And what we show is that this seemingly completely classical problem that can be described and input without any reference to quantum mechanics is quantumly hard and inside a quantum complexity class. So we show it's QMA1 hard and inside QMA. And although these aren't the same complexity class, they are expected to be very close. So this provides kind of a tight upper and lower bound on the complexity of the problem in terms of quantum complexity classes. And we do think we probably can improve this to just QMA1 complete, although there are some details to work out still. Okay, so why should this seemingly classical problem have anything to do with quantum complexity classes? Well, that comes down to a really kind of beautiful insight due to Ed Witten relating supersymmetric quantum mechanics to homology. And the idea here is that we can really use this supersymmetric quantum mechanics to interpolate between quantum computing and homology. I might not have time to talk about this kind of link more in the talk, but just to give you a little bit of insight of where this quantum complexity comes from. Okay, so in the rest of the talk, I'm going to start by giving an outline of quantum complexity theory and a little bit more detail. And then I'm going to define the homology problem more precisely, so to kind of make it mathematically rigorous, exactly what we mean by holes in spaces, and to explain what this promise is that I've mentioned a few times. I'm then going to give an overview of the proof. This won't be kind of a detailed proof, but hopefully it will give you some intuition for how the proof goes. And I'll finish up by talking about some open questions. And if there is time at the end, I'll talk about the link with supersymmetric quantum mechanics a little bit more. Okay, so first up, quantum complexity theory. So in complexity theory, the goal is to understand what kind of resources you need to solve particular computational problems. And the type of computational class we're going to be looking at today is the class that's known as QMA and QMA1. Now, the complexity class QMA is a class of problems where kind of potential solutions can be checked efficiently on a quantum computer. So what this means is, given some problem, let's say you give me some problem and I'm trying to solve it, but I can't solve it. And someone comes along and says, look, this is the solution to the problem. I promise this is a solution. I might say, well, I don't know, do I believe you, do I not believe you? QMA is a set of problems where if they're telling the truth, they can provide me with a quantum state, and then I can run an efficient quantum algorithm on my quantum computer, such that if they're telling me the truth and there is a solution to this problem, my quantum computer will say, yep, accept that solution with high probability. But if they're not telling me the truth and there is no kind of solution to this problem, then no matter what quantum state they give me, my quantum computer will say, no, reject that. That's not a real solution, again, with high probability. So because this is kind of quantum land, we don't have that the quantum computer will tell me to accept or reject with certainty. We allow some small probability of error in both cases. Okay, so this is the class QMA, and this is the class which we know our promise problem is contained in. The other complexity class that I mentioned in the main result is the class QMA1. So what's that class? Well, QMA1 is, as the name kind of suggests, a very minor modification of QMA. And the modification is just that now we only allow error in one case. So what that means is now, if the person who's got this potential solution is telling me the truth and does have a real solution, we're going to say that my quantum computer has to accept that solution 100% of the time. So in the case where there is a genuine solution to this problem, if someone gives me a valid witness, I always have to accept it. We're not going to allow any probability of error. But if there's no valid solution, we're still going to allow that sometimes I might accept an invalid solution. So this sounds like a really minor modification of the complexity class, but it turns out it introduces some subtleties. And the reason for that is because requiring certainty for either case means that we have to be very careful about what universal gate set we're going to use for our quantum computer. So, as I'm sure you all know, there's many different universal gate sets you can pick to run on a quantum computer. And it's known that all these gate sets are equivalent to each other up to small errors. And because normally, with quantum complexity classes, we allow ourselves some probability of error, normally this up to small errors can just be ignored, and we just say any class is equivalent. But here, because we're saying that in some cases we need to get a particular outcome with certainty, we can't just ignore these small errors anymore. We need to actually pay attention to them. And that means that the class QMA1 is not known to be equivalent for different choices of universal gate set. So when we say we're talking about the class QMA1, we actually need to specify what choice of gate set are we talking about. Now, a common choice of universal gate set is the gate set which is Hadamard, T-gate, and C0. I don't know if there's any particular reason that this is kind of the canonical choice, except it was the one used in the first paper. But it's a choice that isn't going to work for us. And it's problematic for us for two reasons. Firstly, the Hadamard gate has this kind of root of 2, this irrational number in. And it turns out that for the homology problem, dealing with irrational numbers is difficult. And equally, this T-gate has a complex number in it. And again, dealing with complex numbers is difficult. So we're not going to use that gate set. Instead, we're going to use a different gate set, which uses the C0 gate and the Pythagorean gate, where, this is called the Pythagorean gate just because, any choice of Pythagorean triple will define such a gate, and any choice of Pythagorean triple would kind of work equally well for our proof, but this is just the simplest one to choose. Okay, and the key thing for us is that all the coefficients in these gates are rational. Yeah.
You said it's difficult to deal with. Difficult to deal with in what sense? Like on a real quantum computer? Or?
No, it's more for the actual homology. So can I explain that when we get to the proof? Because I think it will be clearer then. Okay, so these are the complexity classes that we're going to be interested in. What sort of problems are characterized by these complexity classes? The kind of canonical problem that is known to kind of characterize the complexity class QMA is what's known as the local Hamiltonian problem. And in this problem, you're given some k-local Hamiltonian acting on n spins. And you're given a promise. You're promised that either the ground state energy of this Hamiltonian is below some value A, or it's above some value B, where A and B are separated by some inverse polynomial in the size of the problem. And you're asked, just decide, does this Hamiltonian have a ground state energy less than A or not? And when I say this problem characterizes the complexity class QMA, what I mean is that this problem is inside QMA, so you can solve this problem inside QMA, and it's as hard as any other problem in QMA. So if you have a solution to this problem, you can solve every other problem in QMA as well. Okay, so this is the type of problem that is characteristic for QMA. What about for QMA1? Well, these two classes, the descriptions are very similar, the names are very similar. You might think the characteristic problems would also be very similar, and you'd be completely right. So here, again, the input is some k-local Hamiltonian acting on n spins. But this time the promise is that either this Hamiltonian is satisfiable. So that means either there is the ground state of this Hamiltonian has energy 0, or the ground state energy is bounded away from 0. And again, you're just asked to decide, is the ground state energy of this Hamiltonian 0 or not? Okay, so that's all I'm going to say about kind of an intro to quantum complexity. I'm now going to move on to give a quick intro to homology. So the big question here, I guess, is how do we define holes rigorously? So, in the introduction, I was speaking a lot about deciding whether some space had a hole or not. But I didn't even try and define what a hole is. And intuitively, we all know what a hole is. We can look at this sphere and say, yeah, there's a hole in that up there. But as you get to higher and higher dimensions, you can't look at things. We need to actually be able to rigorously define what we mean by a hole. So kind of building on our intuition, we know that holes are cycles. So this hole is bounded by a cycle, something without boundary. But holes themselves also aren't the boundary of anything. So there's nothing inside this hole. That's why we think of it as a hole. Okay, so we're getting a little bit closer. This is slightly rigorous, but it's definitely still not fully rigorous. So how are we going to use these insights to actually rigorously define what we mean by a hole? We're going to do that using what's known as the boundary operator. And the boundary operator kind of just does what it says on the tin. Given some simplex, if you act on it with a boundary operator, you get out the boundary of that simplex. So we have here a 2 simplex, or a triangle, and when you act on it with a boundary operator, you get out the boundary of that triangle, so the 3 edges that bound that triangle. You can also extend this to kind of chains of simplices by linearity, and what you'll get is if you act on this, the boundary of this triangle, if you act on that with a boundary operator, what you'll find is you get each of these vertices added twice with opposite orientations, so you end up getting 0, which is what we expect. The boundary of a boundary vanishes. Okay, so there are a couple of properties of the boundary operator. The first is that cycles don't have boundaries. That's kind of what we mean by a cycle, something that doesn't have a boundary. So if you act on the boundary act with the boundary operator on any cycle, the output will be 0. And as I said, we also have that the boundary of a boundary vanishes. Okay, so how can we use this to fully rigorously define what we mean by a hole? We've said holes are cycles. So that means that if you act on a hole with the boundary operator, you'll always get out 0. So we have that holes are in the kernel of the boundary operator. We also said that holes aren't themselves the boundary of anything. So there doesn't exist any state V such that C is equal to the boundary operator applied to V. So that means that C is not in the image of the boundary operator. So we put these two things together, and we find that the holes in a complex are given by the kernel of the boundary operator, quotiented out by the image of the boundary operator. So this is kind of the definition of a homology group, and holes correspond to elements of homology groups. And we can now kind of put the problem that we're interested in today in a more mathematically rigorous way. We want to know if the homology group of a clique complex is trivial or not. Okay, so I've said a few times that what we're interested in today is not the decision version of this problem. So we don't just want to know, is the homology group trivial or not? We're interested in the promise version of this problem. So we're interested in a version of this problem where you're given some promise on the solution that makes it a little bit easier to solve. And you might be wondering, what kind of promise could that be? You might be thinking, maybe we're going to promise that either this complex has lots of holes or it has no holes. That seems like kind of a natural generalization based on the promises I explained in the QMA and QMA1 complete problems. But it turns out that's the wrong way to go. And actually, to incorporate a useful promise into this problem, we need to introduce what's known as the combinatorial Laplacian. So the combinatorial Laplacian is given by this expression here, where the delta here is just the boundary operator that I introduced before, and the delta dagger is what's known as the co-boundary operator. So you can think of the boundary operator as giving the boundary of the simplex, and the co-boundary operator as giving like a co-boundary, which is harder to think about, but mathematically well-defined and can be understood with examples. I won't go into the co-boundary operator too much today, but you can just think of it as being the Hermitian conjugate of the boundary operator. What's nice about this combinatorial Laplacian is that it's known that the eigenvalues of, the 0 eigenvalues of the combinatorial Laplacian are in one-to-one correspondence with holes in the simplicial complex. So that means another way of phrasing the question we're interested in answering today is, does the combinatorial Laplacian have a 0 eigenvalue or not? And phrased in this way, it's much easier to see what the right promise is. And the right promise is to say that if there are no 0 eigenvalues, then the lowest eigenvalue is bounded away by 0 by some amount. So the eigenvalues are either 0 or far from 0. We're not going to be able to solve cases where eigenvalues are arbitrarily close to 0 and non-zero. Okay, so this is the promise that we're going to input onto our problem. And it's known that with this promise, this problem is in QMA. I'm not going to talk about the proof that it's in QMA at all, but for people who are familiar with quantum complexity, it's probably kind of fairly straightforward. You can sort of run phase estimation on this operator and use that to solve the problem inside QMA. Okay, so that's kind of as much as I'm going to say about the proof about containment. But in the overview of the proof, in the kind of full overview of the proof, I'm going to be talking about the,
So the size of the complex, the number of vertices, or is the sum of everything? You said the problem is in the size of the complex.
Oh, sorry, no, it's in the size of the graph, not in the size of the complex. So the input to the problem is the graph, not the complex itself. So whenever I talk about kind of this, oh, yeah, no, sorry, that's completely wrong. That should be the size of the graph, sorry, yeah. Okay, so in the overview of the proof, I'm going to be talking not about the overview of the proof of containment, but the overview of the proof of hardness. Okay, so how on earth do you show that a problem is hard for a complexity class? Where when I say a problem is hard for a complexity class, remember, I mean it's as hard as the hardest problem in that class. Well, the way
Tamara, can I ask something back about containment?
Yeah.
That's what I'm going to talk about. Why do you not get QMA1 containment then? Because I have a witness, but if it was the Laplacian was a Hamiltonian, then you've got a zero eigenstate. And where does that go wrong?
So for containment in QMA1, you have to show that you won't have any errors, and it's not enough like for the quantum satisfiability. They can only show it for particular classes, particular gate sets.
Oh, it's the gate set.
I mean, even with different gate sets, it's not clear that because this isn't a nice family of Hamiltonians necessarily, it's not clear that you can. So
I can't run phase estimation because I can give as the witness the eigenstate, the zero eigenstate, and then run phase estimation on that, and you have.
But yeah, you can't necessarily measure it correctly. Yeah. But there's now an updated Gates paper with Seven, one of his PhD students, where they think they can show, but it's work in progress. Okay, so how are we going to show that this is hard? We're going to use the standard kind of characteristic problem for QMA1, and we're going to show that our problem, promised clique homology, is at least as hard as that problem. So we're going to show any solution. If you could solve our problem, you could also solve that problem, and that shows that our problem is at least as hard as that problem. Before I go into exactly how we're going to show that, I'm first going to explain briefly how it's shown that this problem is, that this quantum satisfiability problem itself is hard for complexity class QMA1. So the way this works is by what's known as a circuit Hamiltonian mapping. So given some QMA1 verification circuit, in this paper from 2006, Brave showed a way to construct a quantum circuit such that for yes instances of this, if this quantum circuit accepts on a particular input, there exists a history state which has zero energy with respect to this Hamiltonian, where a history state is just some state that encodes the history of the computation. And he also showed that in no instances, so when the problem corresponding to this QMA1 verification circuit, when it doesn't have a satisfying assignment, every state has high energy with respect to this Hamiltonian.
Is HX the same as HRO?
Yes, sorry, changed notation halfway through, but yeah, no, those should be the same Hamiltonians. So what we have is that in yes instances, there is exactly zero eigenstate for this Hamiltonian, while in no instances, all states of this Hamiltonian are bounded away from zero. So what is this Hamiltonian H Bravi? I'm not going to go through it in any detail, but it basically just encodes the history of quantum computation. So there are 4 types of terms. We have these H-in terms that make sure that at the start of the computation, all our qubits are initialized correctly. We have some terms that correspond to like a clock, and these ensure that there's something in our system that's keeping track of time in the computation. We have these H-prop terms, and these just make sure that the circuit propagates. And H-out basically penalizes no cases at the end of the computation. Now, I'm not going to go through the kind of construction in more detail, except to say that for any quantum circuit you give me, I can build this H-Bravi Hamiltonian out of just this set of Hamiltonian terms. So what you can see here is these Hamiltonian terms correspond to different parts of this Hamiltonian. But the kind of key takeaway here is that just in the same way as you can build a quantum circuit from a finite set of gates, you can build this Bravi Hamiltonian from a finite set of projectors. So the kind of strategy for our proof is going to be to show that we can implement this finite set of projectors within the clique complex of some graph. And then given any circuit, given any Bravi Hamiltonian, I can then build up my graph by putting all these projectors together. So just to say the proof idea once more, so everyone's kind of on the same page. The idea is that we're going to construct a graph where the clique complex has 2 to the n minus 1 dimensional holes. And then we're going to construct gadgets which fill in holes corresponding to the projectors in quantum K-sat. And then given any particular h bravi, I can build up the graph that corresponds to that Hamiltonian by starting with my base graph, and then for every term in h bravi, I add a gadget which fills in the hole corresponding to the state that's lifted by that term in the Hamiltonian. And what this means is that at the end, any remaining holes in the clique complex of my graph are going to correspond to satisfying solutions to the quantum K-sat instance. And if there's no satisfying solutions to the quantum K-sat instance, there's no holes in my graph. And the tricky extra step we're going to do in this work that wasn't done in previous works is that we're going to bound the eigenvalues of the Laplacian in no cases using a technique that's known as spectral sequences. Okay, so first off, what is this? How are we going to build these gadgets? So we're going to start off by looking at the graph, looking at single qubit gadgets. And first off, we're going to look at the graph that encodes a single qubit. So this is the graph that we're going to have encoding a single qubit. And because there's no 3 cliques in this graph, the clique complex of this graph is just the graph itself. So you can think of this as either the graph or the complex. They're just the same kind of object here. And we're going to have that this hole here on the left is going to correspond to the 0 state. And this hole here on the right is going to correspond to the 1 state. Okay, so let's say that one term in our h bravi was a projector that lifted the 0 state, gave energy to the 0 state. How are we going to take the 0 state out of the homology? We're going to do that just by adding some extra vertices to the graph and connecting them up. So what you have here is the kind of outside of this diamond is the cycle that was our 0 state. And we've added some additional vertices into the graph and connected them up in such a way that we've also added these simplices to the complex. And because we've added these simplices to the complex, this 0 state is still a cycle, but it's no longer a hole because it's now a boundary of something. And the thing it's the boundary of is just what we've got here shown in gray. Okay, so that's super nice, super easy. What next? Things get a little bit more complicated when we're not dealing with computational basis states anymore. So what are we going to do? And what we're dealing with is this minus state. So we've got the 0 cycle minus the 1 cycle. What does that mean? And that means we need to construct some object such that this is the boundary of that object. And I think there are lots of different ways to think about this. The way I find it easiest to think about this is to think about kind of applying surgery to this graph so that the cycle that corresponds to this state is really obviously a cycle in the graph. So the way we're going to do that is by adding some dummy vertices to the graph. So for the 0 cycle, we're going to take the x vertex and we're going to split it in 2. And we're going to have an x and an x1. And we're going to do exactly the same thing for the 1 cycle. We're going to split it in 2. We're going to split the x vertex in 2 and label one vertex by x and the other by x1. We're then going to glue these 2 cycles together by saying the x cycles are the same, sorry, the x vertices are the same, the x1 vertices are the same. So let's kind of identify those vertices, and in that way we glue the 2 cycles together. And we then have this cycle. And what's nice about this cycle is it's really obviously a cycle. And that means we can fill it in very easily. Again, we just add some extra vertices, connect them up in such a way that the complex now has solid simplices filling up the cycle we started with. But this isn't exactly the cycle we started with. We've got this extra x1 vertex. And the way we deal with that is that once we've done this procedure, we just say, OK, this x1 vertex is just a dummy vertex. It's really equal to the x vertex. And every vertex that's connected to x1, we just get rid of that connection and instead connect it to the x vertex. It might not be kind of obvious that this necessarily works, but in the paper we demonstrate that this process does work. So this process of kind of adding dummy vertices and then identifying them with the original vertices does indeed lead to us filling in the cycle that we wanted to. Okay, so this gives us a way to fill in the minus state. And kind of all the other 1-qubit states kind of follow on in a very similar way. What about 2-qubit states? So the graph that encodes 2 qubits is given by, as you might expect, 2 copies of the graph that encodes 1 qubit, where we connect up these copies all to all. So I'm not going to draw that graph because it's a mess, but just imagine all-to-all connections between these 2 pictures. Now, the 2 qubit basis states are now given by 4-dimensional generalizations of an octahedron. So this is hard to visualize, but you can sort of visualize it in this picture. So what we've got here is we've got kind of a standard octahedron you all know and love. And then to extend this to a 4-dimensional object, we've added 1 vertex in the center and 1 vertex at infinity and connected them up to every other vertex in the octahedron, but not to each other. And this solid 3D object kind of encodes the boundary of the 4D object we're interested in. I'm going to draw a picture of how you fill this in because I can't draw pictures in 4D. But there is a nice simple method to fill in these 2 qubit basis states. Again, by just adding mediator vertices and edges. How do we deal with entangled states in this picture? So how do we deal with the case where we don't have, or even not even entangled states necessarily, just states that are superpositions of these 2 qubit basis states? The way we do that is by using the fact that every 2 qubit basis state is going to share this edge xx prime. So if you see these 2 graphs, the x and x prime vertex are connected to both the 0 and the 1 state. So any 2 qubit basis state will include this edge xx prime. And what that means is that we can kind of cut open this edge and then glue together along it in order to glue together multiple copies of this 2 qubit basis state. So to make that a little bit clearer, what we've got here is a picture of the boundary of a section of the boundary of this 4-dimensional object. And this is a section of the boundary that includes the edge xx prime. So remember, what we need to do here is cut open the boundary of this object in a way that we can then glue together 2 of these objects together. And the way we're going to do that is by introducing 4 additional dummy vertices. And these 4 additional dummy vertices are used to cut open the xx prime edge, and then they're connected up in such a way that there are no other holes in the complex. We've just cut open the xx prime edge. And we've cut it open in such a way that we've now got a 3-dimensional hole on our 3-dimensional boundary. So just as if you imagine having 2 spheres that you want to glue together, if you cut open a 2D hole in each sphere, you can use that hole to glue together your spheres. Here we have a 3D hole in a 4th sphere, and we can use this 3D hole to now glue together different spheres. So what we have here is the section of the boundary for the 0, 0 state and the section of the boundary for the 1, 1 state. And if we just identify all these dummy vertices with each other, that glues together these cycles, and we then have just a copy of S4 to fill in this entangled state. And having a copy of S4 is nice because we can just fill that in. Whenever we have some copy of an end sphere, it's really easy to just fill that in. And then again, just as in the 1 qubit case, once we've done the filling in procedure, we can then get rid of all the dummy vertices, and we get back to having filled in the cycle we wanted to. Okay, if you look at this list of projectors that we need to implement, you'll probably notice that most of the projectors are actually 3 and 4 qubit projectors. That's tricky because 3 and 4 qubit projectors correspond to 6 and 8 dimensional cycles, which are kind of hard to draw. But we can deal with them in exactly the same way as we've dealt with the 1 and 2 qubit cases. And that's because whenever we have a superposition of 3 and 4 qubit basis states, we can always use the fact that any n qubit basis state, all n qubit basis states, will share n-1 simplices with each other. And we can always cut open that simplex and glue basis states together along that simplex, and that will always give us a copy of Sn, which we can then fill in. And in the paper, we show that this process does remove the correct element from the homology group. And just to come back to your question from earlier about why irrational numbers are difficult. They're difficult because if you have irrational coefficients in your gate set, then what that leads to is you have to add together fractions of cycles, and I have no idea what that means geometrically. So adding together 5 copies of a cycle is like a long process, but it's just 5 copies of a cycle. I know what that means. adding like a quarter of a cycle is, I don't know. So yeah, that's why we need these rational coefficients. Okay, so where are we so far? So to encode a quantum K-set instance into homology, we take the graph, which is n copies of the base graph, connected all-to-all between the copies. And then for each term in the quantum Hamiltonian, we add a gadget to the graph corresponding to that projector. And you can show that the resulting graph will have a hole if and only if the quantum K-set instance is satisfiable.
Is this the same construction as in your original paper with Marcos, or have you had to tweak it slightly?
So far it's similar, except the base graph is much more complicated. So before the base graph was really easy, we never had to go above 3D. But now we have to use a more complicated base graph, which just means everything blows up dimension-wise. I won't actually cover it in the next part, but I can explain it afterwards. It's a little bit subtle, maybe. Okay, so what about the promise in no cases? So as Toby pointed out, so far we've basically proven the same result as we've proven before, albeit in a much more complicated way. How are we actually going to incorporate the promise in no cases? So what we need to do is we need to argue that the low energy spectrum of the Laplacian kind of encodes the quantum K-set Hamiltonian. And that's because if the low energy spectrum of the Hamiltonian is encoding the quantum K-set Hamiltonian, then we can use the quantum K-set Hamiltonian to reason about the lowest eigenvalue of the Laplacian. And in order to do this, we're going to weight the vertices of the graph. So this is why we've shown the homology problem has this complexity characterization for weighted graphs, not for unweighted graphs. And the reason we weight the graph is to basically ensure that the states we lift out of homology don't mess with the rest of the spectrum. So the graph we started with had this homology, and then it had lots of states that were outside homology. When we take states in homology and lift them out, we don't want them to mix with the rest of the spectrum. We want them to stay separated so that we can reason about what's happening in the higher part of the spectrum. So just as in kind of standard complexity theory, we do that by weighting the kind of additional bits we add with a very small parameter, and that will allow us to reason about the spectrum perturbatively. Okay, so as I said, this is a fairly standard technique in quantum complexity, reasoning about things perturbatively. Does that mean that it's kind of all straightforward from here? The answer is no, and that's because there are a couple of subtleties that come up here that you don't kind of get in standard complexity theory. So the first one is, I've said we need to perturbatively compute the spectrum of each gadget that we add to the graph. Okay, so let's just use standard perturbation theory. Except we can't really, because understanding the spectrum of the individual gadgets doesn't require just going to first or second order in perturbation theory. For a k-local interaction, we have to go to order 4k plus 2 in perturbation theory. And that is, we've got 4-qubit interactions going to 18th order in perturbation theory using like the Green's function or Schrieffer-Wolff techniques is not a straightforward thing to do, and it's not something we wanted to try. So we needed to think of a different way to do perturbation theory. Even once you've got the spectrum of the individual gadgets, you're still not kind of home and dry. And that's because I said we need to understand what happens when we combine many gadgets together. And this is, again, a difficult problem, because adding new gadgets to the graph doesn't correspond to adding positive terms to the Hamiltonian. It corresponds to adding general terms to the Hamiltonian that aren't positive semi-definite. So they might decrease the energy of they might decrease the energy of the Hamiltonian. So that means, again, we can't use like standard techniques like martingale methods or ground state projectors in order to understand what happens when we combine many gadgets together. Okay, so we can't use standard techniques from quantum information theory to do this final step. What are we going to use instead? We're going to use tools from algebraic topology. And in particular, we're going to use what's known as spectral sequences. So the idea in a spectral sequence is it's a way to perturbatively compute the homology of a simplicial complex. So given some simplicial complex, which, for now we're just going to say, given a simplicial complex where some vertices are weighted by much less than others, it might be that you can't compute the homology of the complex simply, but maybe by ignoring the perturbations, you can start computing the homology, and then you can steadily add in more information and perturbatively compute the homology. And this is a technique that's used in algebraic topology. What's really important for us is that from the spectral sequences, you can also deduce information about both the eigenvalues and the eigenvectors of the combinatorial Laplacian. So for us, we don't actually want to compute the homology perturbatively. We know the homology of each gadget is really simple. But we do want to understand the eigenvalues and eigenvectors, and we're going to use spectral sequences to do that. Okay, so there's only 5 minutes left, so I'm not going to explain spectral sequences in loads of detail, but I'm going to kind of go through one simple example that will hopefully give you an idea of how this works. And yeah, let's see how that goes. Okay, so this is not a gadget that actually appears in the paper at all, but it's a nice simple example to work through. Sorry, this example does appear in the paper, but it's not needed for the proof. It's just there as a nice example. So what we have here is we're going to think of the vertices on the outside of this hexagon as our qubit vertices. And these are weighted by weight 1. So these are nice ordinary weight vertices. Then the vertices on the inside are weighted by weight lambda, where lambda is much, much smaller than 1. So we're going to think of these vertices as being a perturbation to our graph. And you can see that the simplices that are induced by these vertices pick up a weighting from the vertex. So a triangle that has 1 vertices and 1 lambda vertex has weighting lambda. If it has 2 lambda vertices, it has weighting lambda squared, and so on. Okay, so how do you use this weighting to compute the spectral sequence? So we're going to do this by basically splitting up the complex. So we split up the complex along kind of 2 axes. One axis is what I've called the perturbation level. So the 0th level of this axis contains simplices that have no perturbed vertices in them. The first level contains simplices that contain a single perturbed vertex, and so on to higher and higher numbers. On the other axis, we have the dimension of the simplex. So we have 0 simplices, 1 simplices, 2 simplices, and that's all we have to worry about in this example. And the idea here is that rather than trying to compute the homology all at once, we're going to compute the homology bit by bit. So first of all, we're going to compute the homology where we just pretend that the perturbed vertices don't partake in the homology at all. So we're just going to say that our boundary operator here is just the qubit boundary operator. I'm going to pretend the mediator vertex boundary operator doesn't exist. And we're going to compute the homology groups of each of these terms with just this boundary operator. Okay, I won't go through this in loads of detail because we're short on time. But if we use, maybe this is an example, all these vertices here are qubit vertices. So when we compute the homology of this term, this 1, 0 term in this graph, it's really obvious to see that the homology of this is just the outside cycle. Because you can just see that's the hole in the graph. And indeed, that's what you get when you compute the spectral sequence. In this term, you have just this cycle. This term also looks like it's a cycle, but this term contains both qubit vertices and gadget vertices. So even though this looks like a cycle, when you apply the qubit boundary operator alone, it turns out this isn't a cycle. And it turns out the homology of this part of the graph is trivial. There is no homology. I won't go through all the examples, but I'm happy to talk through it afterwards. But when you compute the homology of each element of this graph using this qubit boundary operator, this is what you get out. Okay, so this is kind of the first level of our approximation. We forgot about the mediator vertices and just looked at the qubit vertices. We're now going to go to the next level of approximation. Here we're going to forget about the qubit vertices and just look at the mediator vertices. And if you just look at the mediator vertices, what you're doing in this graph is kind of moving diagonally, because changing the mediator vertices moves you not up and down in this graph, but diagonally. And again, okay, I won't go through this in detail, but if you look at the homology of each of these each of the pictures here in terms of this operator, what you'll find is that nearly all of them have trivial homology. So after we've applied kind of the approximation of compute the homology of these pictures, we end up getting to a next level of approximation where we now have we now only have 2 kind of surviving elements. And these surviving elements are just kind of this loop that we started with, which just contains qubit vertices and this kind of core state, which just contains the triangles that don't include any qubit vertices. So this is triangles formed entirely out of mediator vertices. Okay, so now we're going to do another level of approximation. We're now going to say, okay, we've got both mediators and qubits. Let's use them both a little bit. And we're going to do that by saying, okay, we're going to add a mediator vertex and take away a qubit vertex and add another mediator vertex. And that kind of moves you in this graph up and down and up again. But if you do that movement to both of these, you can see both of these are mapping to nothing. There's nothing there for them to map to. So that means when we apply this level of approximation, nothing happens because there's nothing there for either of these to map to. So the third page of our approximation is just the same as the second page. Now we're going to do another level of approximation. We're going to say, okay, we're not just going to go up and down once, we're going to do it a couple of times. So we're going to go add a mediator vertex, take away a qubit, add a mediator, take away a qubit, add a mediator. When we do that, we find that things in this part of the graph map to things in this part of the graph. And not only do things here map to things here, it turns out that this state actually maps to exactly this state. And what that means is that both these states have trivial homology, because this is the image of something, and this doesn't map to 0. So we find that the fourth page of our approximation is there is no homology. And that's exactly what you'd expect, because you can just see, you look at this complex, there is no homology. So that's what we found, which is what we want to find. But the really nice thing is that what is shown in Foreman's paper is that if you take elements of each page of the spectral sequence and quotient out everything that still survives to the next page, what you have is a space of eigenvectors with eigenvalue lambda to the 2j. So things which are on this page but not on this page are O1 eigenvalues. Things which are on this page but not on this page are O lambda to the minus 2 lambda to the 2 eigenvalues, and so on and so on. And it tells you not just about the eigenvalues, but it also gives you information about the eigenvectors. And using this, we can understand both the eigenvalues and the eigenvectors of the individual gadgets. So I'm not going to go through a full gadget proof, but Robbie in the paper worked out kind of very, very complicated calculations for the actual gadgets we use, and he's able to demonstrate a lemma which really characterizes the spectrum of the individual gadgets. And with the understanding from that, we can argue that in no cases, every state must have overlap with the excited states of at least one gadget. That's kind of an obvious thing you can get. The more difficult part is to argue that any low energy state of the Laplacian has low overlap with the excited states of every gadget. And I'm not going to go through the proof of that at all, but it's all in the paper. Again, yeah, Robbie really kind of worked that out, and please look at the paper if you're interested. And that's as much as I'm going to say about the proof, but hopefully give you some idea of how it works. And since I'm out of time, I'll just leave the open questions up, and I'm happy to take any more questions.